Well, thanks so much for the introduction and for inviting me to be here today. And I'm looking forward to sharing some work from my group where we've used the excited state lifetimes of nitrogen vacancy centers in individual nanodiamonds to measure temperature with a combination of both high spatial and temporal resolution. So before delving into the details of that work, just to place it in the broader context of what my group works on, I'll first very briefly highlight some other current projects in my group, including several that I won't have time to discuss further today. So we're largely focused on using luminescent materials to probe temperature and thermal transport, particularly in situations where these materials offer unique advantages or where more conventional methods aren't feasible. So one major ongoing project in my group is developing an optical super resolution nanothermometry technique, which involves using far field optics to map temperature with spatial resolution below the diffraction limit. We also have another project focused on separating thermal and non-thermal contributions in the context of plasmonic photocatalysis. The project that I'll focus on today involves using the excited state lifetimes of nitrogen vacancy centers in individual nanodiamonds to measure temperature with spatial resolution below 100 nanometers, as well as temporal resolution on the order of tens of nanoseconds. And finally, we're also using this same material system, nitrogen vacancy centers in nanodiamonds, to study heat transfer in rarefied gases. And that work is done in collaboration with Nick Vemavakis, who's also at Rochester in the Institute of Optics. As I said before, for the sake of time, I won't touch on most of these projects further today, and I'll instead focus on our time-resolved nanoscale temperature measurements using nitrogen vacancy centers in single nanodiamonds. And as I'll show later on, this is really the project where our lab's PARC NX10 AFM plays a central role, so I think it fits very well with today's event. So before getting into all the details of that project, I'll first give some broader motivation for why we need to develop new nanothermometry techniques. One area where thermal management continues to be a huge challenge is in electronics, and we experience that in a macroscopic sense when our laptops or smartphones overheat. But the origins of these problems are really at the nanoscale, and that's because transistors now have feature sizes on the order of 10 nanometers, and so that means that hotspots have shrunk to the nanoscale as well. Another area where heat transfer is important is energy, although when we think about heat transfer and energy, we might typically think of large-scale systems like steam power plants or internal combustion engines. But it turns out that there are other areas like lighting where heat transfer at smaller scales is important. And to give one example, as we've shifted from incandescent light bulbs to LEDs, the thermal challenges associated with lighting have shifted to the nanoscale. And that's because LEDs are semiconductor devices whose active regions contain many thin layers that are often only a few nanometers thick. And although LEDs are energy efficient compared to incandescent bulbs, they still typically waste at least 10% or more of their input energy as heat, which can lead to big performance and reliability losses. On the other hand, there are also applications where rather than being parasitic, localized heating can actually be desirable if it's carefully controlled. And so one example there is thermal cancer therapies, where nanoparticles are embedded in cancerous cells, and then a laser is used to heat the nanoparticles with the goal of killing the cancer cells while leaving the healthy tissue intact. Another example where controlled localized heating can be desirable is in some next generation hard drive technologies. One example there is heat-assisted magnetic recording, where localized heating is used to temporarily change the properties of the magnetic recording medium to ultimately achieve higher storage densities. And another example is phase change memory, where localized Joule heating is used to switch a phase change material between two different states. And so next, to understand how the inability to measure temperature at the nanoscale specifically limits these technologies, I'll discuss a couple examples in a bit more detail. So heat-assisted magnetic recording, or HAMR, is, as I said, a next generation hard drive technology, and it's expected to more than double storage densities. The basic idea behind HAMR is to plasmonically excite this gold lollipop-shaped structure known as the near-field transducer, or NFT, and couple energy from the 30 nanometer peg across a gap and into the recording medium below. And the idea is that this energy then heats the recording medium, which temporarily lowers its coercivity. And this allows for smaller bit sizes and ultimately higher storage densities. But one major challenge for HAMR is that it's known that instead of heating the recording medium, instead significant parasitic heating of this 30 nanometer peg can happen instead. And degradation of the HAMR peg can cause entire HAMR drives to fail. And so again, it's thought that the cause of this degradation is overheating. But right now, there's no way to actually measure that peg temperature during operation. Phase change memory is another new hard drive technology that's expected to improve storage densities. And here the idea is to use joule heating to switch a nanoscale amount of a phase change material, typically a chalcogenide glass, between a resistive amorphous state and a conductive crystalline state. And the way that this works is that to go from crystalline to amorphous, the phase change material is heated above its melting temperature and then quickly quenched to lock in the amorphous phase. And to go from amorphous to a crystalline, the phase change material is heated above what's called the crystallization temperature, which is lower than the melting temperature, and then held there until it recrystallizes. And so one challenge for these phase change memory devices is that the crystallization temperature for these nanoscale amounts of phase change material can differ significantly from the bulk value. And some estimates suggest by hundreds of degrees. But again, there's really no existing thermometry technique that can measure this crystallization temperature. So stepping back for a moment and starting to think more broadly about the applications that I've just discussed, there are certain recurring themes that start to emerge in terms of the types of nanoscale systems where we'd like to be able to measure temperature independent of particular technologies or devices. And so one theme is that we'd like to be able to measure the temperature along stacks of thin films, whether that's in active region of LEDs or related optoelectronic devices, or in the recording medium in heat sink layers beneath the HAMR peg. Another theme is that we'd like to be able to measure the temperature of nanoscale hotspots, like the HAMR peg or the unknown crystallization temperature in nanoscale phase change memory devices. And so the thin films is something that my group also works on, but for today, I'll focus specifically on measuring the temperature of nanoscale hotspots, since that's the particular challenge that the work I'm presenting today addresses. And before getting into the details of how we actually perform those measurements, one question I want to discuss is why we specifically need experimental tools to do this. Because clearly these systems are very small and in many cases quite complex. But why couldn't we just use a sophisticated model to calculate the temperature rise? And so it turns out that one reason is that the classical laws of heat transfer that you might learn in an undergraduate course, like Fourier's law, don't always hold up at the nanoscale. And we can understand that by considering an example here of a heat generating sphere in an infinite medium. And so if we zoom into this material, we'd find that there are energy carriers, for example, phonons, that collide with one another, and in between collisions, they travel an average distance that we call lambda, or the mean free path. And in this classical Fourier's law case, the diameter d of our sphere is much larger than that mean free path lambda. And so that means that we get this kinetic theory expression for the thermal conductivity that says K is equal to 1/3 CV lambda, where C is heat capacity and V is velocity. And so we can then use this expression for the thermal conductivity along with Fourier's law to calculate the temperature rise of our sphere. But now let's consider a heat generating nanosphere whose diameter d is much, much smaller than that mean free path lambda. So in this case, it turns out that Fourier's law no longer applies. And we instead have to use the Boltzmann transport equation to solve for the temperature rise of our sphere. And so in this very simple case, we can get an analytical solution. And what we find is that the ballistic temperature rise is much larger than what Fourier's law predicts when the diameter of our sphere is much smaller than that mean free path lambda. And so in more complicated nanoscale geometries and systems, we can again expect these kinds of deviations from classical laws, but the details really aren't that well understood. And so that's why we really need experimental tools to study and account for these kinds of effects. So now, starting to think in more detail about thermometry techniques, we can really divide existing techniques into two broad categories. And one category is optical non-contact methods, and I'll show a few specific examples here. So thermal radiation, both infrared and visible, provides a convenient method to map temperature with well-understood temperature-dependent physics. It also works well both near room temperature as well as at much higher temperatures. There are also many laser-based techniques, including thermoreflectance techniques like time domain and frequency domain thermoreflectance, which have really transformed our understanding of a lot of important thermal transport problems. There are also other laser-based techniques, including Raman thermometry and conventional luminescence-based temperature mapping, in contrast with some of the more unconventional methods that I'll show later on. And so these optical non-contact techniques certainly have numerous advantages, but they are all ultimately limited in terms of spatial resolution by optical diffraction. And so to circumvent the diffraction limit and achieve the nanoscale spatial resolution that we're looking for, one option traditionally has been near-field and contact-based techniques. And historically, these techniques have been subject to challenges involving unknown thermal contact resistances between the probe tip and sample, and parasitic heat sinking by the probe, which can make it difficult to accurately extract the true sample temperature. That said, in recent years, there have been some exciting advances in terms of overcoming these challenges. One example is recent work from a group at Michigan, where they performed scanning thermal microscopy measurements in ultra-high vacuum and simultaneously measured the apparent sample temperature and tip sample thermal contact resistance, which let them map temperature with about 7 nanometer spatial resolution. And so this is a really nice approach to mapping temperature with very high resolution, but nonetheless, there are still many other situations where physically contacting the sample or operating in vacuum isn't possible. And so we want to develop approaches that offer solutions in those situations, which then leads us to ask the question, is there any way that we can somehow use far-field optics to beat the diffraction limit and measure temperature at the nanoscale? So one way to measure temperature at the nanoscale using far-field optics is to take advantage of the temperature-dependent luminescence emitted by an individual nanoparticle. And I'll emphasize that this approach only allows for measurements at a single spatial point. But for situations where we just need to know the temperature at a single critical location, which is exactly the case with these nanoscale hotspot applications, then this approach works very well. And so the basic idea is that we take a single nanoparticle and place it at the exact location on the sample surface where we want to measure the temperature. And this is actually where our AFM comes in, and so I'll get back to that a bit later. And the idea is that we then excite the nanoparticle with a laser and measure the temperature-dependent luminescence that it emits in order to determine the sample temperature. And because the nanoparticle is very small, this minimizes issues of parasitic heat sinking and thermal contact resistance so that the nanoparticle can accurately report the true sample temperature. And now I'll drill in on for just a second on how we're getting nanoscale temperature information, even though we're still using a diffraction limited laser. And so it's true that the diameter of our excitation laser beam is still diffraction limited. But the key is that the luminescence and therefore the thermal information comes only from the nanoparticle, whose size is, of course, much smaller than that diffraction limited laser beam. And so as long as we're sure that we're only probing one single particle at a time, then the spatial resolution of our temperature measurement is governed by the nanoparticle size. And when we perform these measurements, we ensure that the nanoparticles are spaced sufficiently far apart on average such that their diffraction limited emission spots don't overlap. All right, so I'll now circle back just very briefly to one of the motivating applications that I talked about earlier, which involves measuring the unknown crystallization temperature in nanoscale phase change memory devices that use Joule heating to switch back and forth between a resistive amorphous state and a conductive crystalline state. And so if we look at the switching process in a bit more detail, it turns out that the set process, which is where the phase change material is held just above that crystallization temperature, that occurs on a fast time scale of about 10 nanoseconds. And so that means that if we want to measure this crystallization temperature, then not only do we need a thermometry method that can give us spatial resolution of about 50 nanometers, but we also need a technique that can give us temporal resolution on the order of 10 nanoseconds or so. And so more broadly, it turns out that for many nanoscale thermometry applications, we need measurements with high temporal resolution as well. And we can understand that by thinking about estimating a thermal diffusion time, which tells us how long it'll take an object to heat up or cool down. And so the thermal diffusion time goes as L squared over alpha, where L is the characteristic length scale and alpha is thermal diffusivity. And so even though we might not generally think of heat transfer as a fast process, by looking at the scaling, we can actually see that in nanoscale systems, the time scales associated with heat transfer can actually become quite short. All right, so next I'll introduce the specific materials system that's the basis of the measurements I'll show today, which is nitrogen vacancy or NV centers. And NV centers are bright photostable fluorescent defects that are found in both bulk diamond and nanocrystalline diamonds that consist of a substitutional nitrogen atom and an adjacent vacancy. And these NV centers have applications in a number of areas, so I'm sure at least some in the audience have heard of these defects before. These applications do include thermometry. The most common NV center thermometry method that's been demonstrated is something called optically detected magnetic resonance, or ODMR thermometry, where resonant microwave pulses are used to control the NV center spin state, and then the temperature-dependent zero field splitting of the ground state spin triplet can be read out from the emitted fluorescence. And so this is a well-established method that's been used in a number of interesting applications, but nonetheless, there are a few drawbacks. So first, ODMR thermometry requires using a microwave antenna, which can cause parasitic heating or damage sensitive samples. It also has temporal resolution that's limited to about 10 microseconds, and it isn't feasible above about 700 Kelvin due to the loss of the fluorescent signal at high temperatures. There are also some all-optical methods, meaning methods that don't require a microwave antenna, that have been demonstrated using temperature-dependent features of the NV center fluorescence spectrum, but these are also limited in terms of temporal resolution and temperature range. So with the goal of measuring temperature using an all-optical method that has higher temporal resolution and the potential to go to high temperatures, we were interested in the possibility of using the excited state lifetimes of NV centers, or in other words, how long it takes the emitted NV center fluorescence to decay after the excitation laser is removed as a thermometry signal. And in general, excited state lifetimes decrease with temperature because at higher temperatures, there's a greater probability of phonon-assisted non-radiative relaxation. So excited state lifetime thermometry has been demonstrated using a number of other luminescent materials, including upconverting nanoparticles, which is something that I actually worked on during my PhD. For most of these materials, all the existing measurements have been performed using ensembles or large groups of these nanoparticles, which means that these measurements lack the nanoscale spatial resolution that a single point measurement can provide. And in many cases, the temperature range is also limited because these materials are targeted for biological applications. And so these upconverting nanoparticle measurements did use single particles, but because upconverting nanoparticles have long lifetimes on the order of hundreds of microseconds to milliseconds, they lack the high temporal resolution that we're looking for. NV centers, on the other hand, are known to have room temperature lifetimes on the order of tens of nanoseconds. So they're promising in terms of temporal resolution, but there's been very limited work looking at how these lifetimes vary with temperature. And so one study that you see on the left looked at a single NV center in bulk diamond and found that the lifetime was independent of temperature below about 550 Kelvin and then decreased at higher temperatures. Another study, which is what you see on the right, looked at large ensembles of many nanodiamonds, each containing many NV centers, and found continuously decreasing lifetimes between 300 and 700 Kelvin. But we were interested in NV centers in single nanodiamonds, since again, using single nanodiamonds can give us single point temperature measurements with high spatial resolution, and that is something that had not been looked at before. So the first step in measuring the temperature dependence of NV center lifetimes in single nanodiamonds was to figure out a reliable way to distinguish single nanodiamonds from small aggregates that can form when we disperse these nanodiamonds. And because of the variable number of NV centers per nanodiamond and differences in surface defects that can reduce emission intensity, we find that the brightness of a diffraction limited emission spot is unfortunately not a very reliable way to distinguish single nanodiamonds from aggregates. So what we do instead is we deposit nanodiamonds on substrates with fiducial markers and use scanning electron or atomic force microscopy to first identify single nanodiamonds. And then we can later find those same nanodiamonds using our optical microscope. And we can see that, for example, one of the single nanodiamonds shown in the image on the bottom left is actually much brighter than one of the doubles. And so this kind of cross-identification is very important to be sure that we're really only measuring single nanodiamonds. So then to measure the excited state lifetimes of single nanodiamonds, we use a method called time-correlated single photon counting, which involves detecting single photon arrival times over many repeated excitation and decay cycles in order to build up a histogram of photon arrival times that's equivalent to the lifetime decay curve. And so we have a time-correlated single photon counting module that's part of a larger custom scanning confocal microscope, which is shown schematically in the bottom left here. And it also includes a thermal stage that lets us perform measurements from room temperature up to about 500 Kelvin. And then in the bottom right is a picture of that system that we built in my lab at Rochester. All right, so we measured the excited state lifetimes of multiple individual nanodiamonds on both silicon and glass substrates between room temperature and about 500 Kelvin. So looking first at representative lifetime decay curves for a single nanodiamond on a silicon substrate at room temperature and close to 500 Kelvin, we can see that the lifetime indeed decreases with temperature. And we fit the lifetime decay curves with a double exponential and get a longer decay component that's typically 25 to 30 nanoseconds at room temperature, and a shorter decay component that's typically less than 5 nanoseconds. And this agrees well with other room temperature measurements. So we can then plot the average lifetimes as a function of temperature for all 5 nanodiamonds that we have here. And we see that the average lifetime indeed decreases with temperature for all the nanodiamonds, with an average decrease of just over 30% over this temperature range. And while the lifetime values show some variation from one nanodiamond to another, we do find that the change in the lifetimes is more consistent among nanodiamonds. We also find that for the majority of nanodiamonds we measure, the change in the lifetime with temperature can be approximated as linear over this temperature range, which lets us estimate uncertainties and sensitivities that I'll show in just a moment. And then finally, we also see from the right-hand figure that the majority of the temperature dependence comes from the longer decay component. And we repeated all these same types of measurements for nanodiamonds on glass substrates, and I won't show those results for the sake of time, but they're largely very similar, with the main difference being that the lifetimes are slightly longer on average. So this summary table here shows both the average percent decrease in the lifetimes over the temperature range where we performed our measurements, and the temperature uncertainties and sensitivities that we estimate using the linear approximation for the change in the average lifetime with temperature. And so we calculate uncertainties of plus or minus a few degrees and sensitivities on the order of tens of kelvins per roots, which are reasonable for the applications that we're interested in. And also emphasize again that this single nanodiamond lifetime thermometry can work in situations where other methods would not. So specifically situations requiring a combination of all optical probing, high temporal resolution or higher temperature measurements, since these time-correlated single photon counting measurements work very well for low emission intensities. And so finally, one question that naturally arises with single nanoparticle thermometry techniques is how we can place a single nanoparticle at the exact location on the sample surface where we want to measure temperature. Because of course, that is extremely critical for practical applications. And so to address that need, over the last few years in my lab, we've used our Park NX10 AFM to develop the capability to manipulate individual nanoparticles, including but not limited to these nanodiamonds, and place them on a sample surface at exactly the location that we would like. And as we've sort of heard from others, we do this by essentially hacking the nanolithography mode of our AFM to move the nanoparticles along the desired trajectory. So with this approach, we can make microscale movements, which is how you see the patterns, that you see here were formed. But then we can also do much finer movements, so easily down to tens of nanometers. And so now if we combine this type of AFM nanomanipulation with the temperature-dependent excited state lifetimes of these NV centers in individual nanodiamonds, then we have a really nice way to do far-field optical single-point thermometry with both high spatial and temporal resolution. And so now that we've essentially proven this capability, we're looking forward to applying it to some of these interesting, motivating applications that I mentioned. All right, so to summarize, we've measured the excited state lifetimes of NV centers in individual nanodiamonds between room temperature and about 500 Kelvin, and we find a consistent decrease in the lifetimes with temperature, which means that the signal can provide single point temperature measurements with both high spatial and temporal resolution. And so we also have a paper on this work that came out in Applied Physics Letters late last fall. So if you're interested, you can certainly find more details there. Finally, I'd like to acknowledge our current funding sources, as well as the members of my research group, and in particular, my PhD student, Dinesh Vamidi, who led this work that I showed today. With that, thank you for your attention, and I'd be happy to answer any questions.
Okay. Well then, yeah, thank you, Professor Pickel. We really appreciate you taking your time to do this for us. And yes.